we have already discussed the differentiation of a complex function. So we have seen that a complex function with a derivative defined called an analytic function, and we have found an easy method for finding the derivative of an analytic function. The function is not analytic, then the derivative does not exist. So if the function is analytic, the derivative can be easily found as dou f dash of z is equal to dou f by dou x itself. So now we define the integration of a complex function. So we know that integration is nothing but the continuous summation, and we already know the integration of a real function. So suppose this is the real axis x, and the function f of x is defined over here. So it's a curve. So the integral of this function from the point x0 to the point x is the area under the curve. So analogous to this, we can define the integration of a complex function. So here suppose we have z over here and f of z is defined over here, and suppose we have a contour c over here. So the integral of this complex variable over a contour and complex plane so can be defined in a close analogy to the integration of a real function which is integrated along the real axis. So here we divide the contour from the point z0 to the point z into n intervals by taking n minus 1 intermediate points. So we have n minus 1 intermediate points, 1, z2, z3, etc. up to zn minus 1 on the contour. So then the integral is equal to the continuous summation. So these are all rectangles. So suppose zeta I is a point defined on the curve between zi and zi minus 1. Okay, z1 and z0 ഇടയിലുള്ളത് zeta 0, ഇവിടെ zeta 1. So zeta is a point defined, zeta I is a point defined on the curve between zi and zi minus 1. So then the summation, continuous summation Sn is equal to summation I goes from 1 to n. So this point is zeta I and this curve is nothing but f of zeta I. So the central point is zeta I. So this height is f of zeta I and the breadth is zi minus zi minus 1. Okay, so this is f of zeta I, which is the length, and the breadth is this. So this is f of zeta I. So this is for the first rectangle, it is z1 minus z2, and the first part is f of zeta 1. So we can write it as zi minus zi minus 1. So I goes from 1 to n. So the end point is z, which is equal to zn. Okay. So now we let n tends to infinity over here. That means we're dividing this contour into infinite number of intervals. So that is, every interval is very small and therefore it corresponds to a rectangle. So n tends to infinity, then zi minus zi minus 1 tends to 0 for all I. Then limit n tends to infinity, Sn is nothing but the integral from z0 to z f of z dz. So this RHS here is called the contour integral of f of z along the specified contour C from z equal to z0 to z equal to z. So this is the contour integral of the function f of z over the contour C, which is starting from the point z0 and ending on the point z. Okay, so this integral I is the contour integral. So now we can write integral z1 to z2 f of z dz, the contour integral of f of z from z1 to z2. So we know that the point z1 can be represented as ordered pair x1, y1 and z2 as ordered pair x2, y2. So now we have to represent this integral in terms of x and y. And we know that f of z is nothing plus but u plus iv, and z is x plus iy, and therefore dz is dx plus I dy. So this can be written as the integral x1 y1 to x2 y2 u dx minus v dy plus I into integral x1 y1 x2 y2 v dx plus I u dy. So I is there, and so this shows that the complex integral is the complex sum of real integrals. So the complex integral can be represented as an ordered pair of two real integrals. So here the path joining x1 y1 to x2 y2 is specified with the contour C. So now we can do some examples. The first one is that find the contour integral z to the power n dz over C, where C is a circle of radius r greater than 0 around the origin z equal to 0 in the positive mathematical sense. So positive mathematical sense means the anti-clockwise direction. Okay, so this is the origin and we have a circle having radius r, and which is in the anti-clockwise direction. So this is our contour C. And for this we have to use the parametric form. So we know that in the parametric form z is equal to r e to the power I theta, and therefore dz is equal to I r e to the power I theta d theta. So we are taking derivative of z with respect to theta. R is a constant here. So now we have two cases. The first case is for n not equal to minus 1. So there are, in the first case n not equal to minus 1, n as an integer, but so in all those cases n is an integer. Okay, so but n not equal to minus 1. So this integral over C z to the power n dz can be written as r e to the power I theta whole to the power n, and dz is I r e to the power I theta d theta. Okay, so we can take r to the power n plus 1 outside, and I is also a constant which can be taken outside. We can have e to the power I n theta into e to the power I theta, that is e to the power I n plus 1 theta d theta. So theta for a circle theta varies from 0 to 2 pi. So we have I into r to the power n plus 1. So the integral of e to the power I n plus 1 theta is e to the power I n plus 1 theta divided by n plus 1. So we have to apply the limits 0 to 2 pi over here. So we have I r to the power n plus 1 divided by n plus 1, applying the limits e to the power I 2 pi, that is e to the power 2 pi I is 1, e to the power 0 is again 1, 1 minus 1 is 0. So because the 2 pi is the period of this function, e to the power 0 is equal to e to the power 2 pi I. Okay, now for n equal to minus 1, the integral is z to the power minus 1 dz, that is integral 1 over z dz. So we can substitute z here, r e to the power I theta, and dz here, I r e to the power I theta, d theta. Okay. So cancelling similar terms, we can have I outside and d theta. So 0 to 2 pi. So 2 pi I is the answer. Okay. So for n equal to minus 1, the result is 2 pi I, and when n not equal to minus 1, the result is 0. In both cases, the integral is independent of the radius. In both cases, the integral is independent of the radius of the contour C, which is R. Okay. So now we can do the same problem, integrate z to the power n dz over another contour. So the contour here is a rectangular contour with corners z1, z2, z3 and z4. So now we can do the problem for n not equal to minus 1. So closed integral z to the power n dz over the contour C can be written as the integral z to the power n dz for the line 1 plus integral z to the power n dz for the line 2, integral z to the power n dz for the line 3 plus integral z to the power n dz for the line 4. So this closed integral can be written as the sum of 4 line integrals, and the first line is a point joining the points z1 and z2. So integral z to the power n dz is z to the power n plus 1 divided by n plus 1, starting from the point z1 to the point z2, and this integral is again z to the power n plus 1 divided by n plus 1. So applying the limits from z2 to z3. And for the third line, the limits are z3 and z4, and for the fourth line the limits are z4 and z1. So please calculate this, please apply the limits, and you can find that the result is 0, because each corner point appears as the upper limit and also as the lower limit. Z1 as the lower limit, Z1 as the upper limit. Similarly for all other 3 points. But for n equal to minus 1, we can find the integral over C, 1 over Z dz is the integral along the 4 lines. So the integral of 1 over z is log z. So log z from z1 to z2 plus log z plus z2 to z3 plus log z plus z3 plus z3 to z4 plus log z from z4 to z1. So here z is a complex function, and therefore we can set log z can be written as log r e to the power I theta, which is log r plus log e to the power I theta, that is log r plus I theta. Okay, now applying the limits, we get log r2 plus I theta 2 minus log r1 plus I theta 1 plus log r3 plus I theta 3 minus log r2 plus I theta 2 plus x8. So here the corresponding real parts of the logarithm cancel. So log r2, log r1, log r3, log r4 cancels. But the imaginary parts involve the increasing of arguments of the points from z1 to z4. So when we come back to the point z1, ഇങ്ങനെ z1, z2, z3, z4 again z1 ലേക്ക് എത്തുമ്പോൾ ഒരു കംപ്ലീറ്റ് റൊട്ടേഷൻ ആയി. അപ്പൊ നമ്മുടെ തീറ്റ എന്ന് പറയുന്നത് നമ്മൾ പറഞ്ഞൊരു മൾട്ടി വാല്യൂഡ് ഫംഗ്ഷൻ ആണ്. സോ 2 pi is added once we complete the rotation. So we have this term like this, and the fourth integral, which is log r1 plus I theta 1, should be written as log r1 plus I into theta 1 plus 2 pi. അപ്പോൾ നമ്മളൊരു റൊട്ടേഷൻ കംപ്ലീറ്റ് ചെയ്തുകൊണ്ട് അതിന്റെ കറസ്പോണ്ടിങ് ആർഗ്യുമെന്റ് എന്ന് പറയുന്നത് തീറ്റ 1 അല്ല, തീറ്റ 1 plus 2 pi ആയിരിക്കും. So calculating this, you will find that the result is equal to 2 pi I. So when we come back to the first corner z1, its argument has incremented by 2 pi due to the multi-valuedness of the logarithm. So 2 pi is left over as the result. So the value of the integral involving the multi-valued function must be that which is reached in a continuous fashion on the path being taken. We can say that the closed integral z to the power n dz equal to 0 and closed integral 1 over z dz equal to 2 pi I for rectangular as well as circular contours. Okay, thank you.